Our solar system spans roughly 6 billion miles from the Sun to Neptune. The 4 stars in this video would consume all of it. Planets, moons, asteroid belts, without even noticing. The star at number 1 would swallow everything out to Saturn's orbit and still not be done. These are 4 real, observed, peer-reviewed stars, counted down from enormous to almost impossible, each entry larger than the last. By the end, your sense of scale will be broken. The number 1 entry is hidden inside a dense stellar cluster nearly 20,000 light-years away, and its measured size appears to exceed what current models of stellar evolution say should even be possible. We start at number 4, with a dying hypergiant already large enough to engulf Jupiter's orbit. In the 4th place, VY Canis Majoris stands as a red hypergiant unlike anything in our immediate cosmic neighborhood. Located about 3,900 light-years away in the constellation Canis Major, this star's measured radius is staggering, roughly 1,420 times that of the Sun. To translate that into the familiar scale of our own solar system, VY Canis Majoris would stretch its surface past the orbit of Jupiter at 5.2 astronomical units. Mercury, Venus, Earth, Mars, and the entire asteroid belt would all be lost deep within its outer layers, with Jupiter's orbit just barely inside the star's swollen edge. What sets VY Canis Majoris apart isn't just its size, but the violence of its final years. This star is shedding its mass at an extraordinary rate, blasting out arcs, loops, and tangled filaments of gas that form a chaotic, asymmetric nebula. The Hubble Space Telescope has captured these structures in detail, revealing a history of repeated catastrophic outbursts, some within the past 1,000 years, others as recent as a few decades ago. Astronomers describe it as a star in terminal instability, a living warning sign that the end is near. Within the next 100,000 to 500,000 years, VY Canis Majoris is expected to explode as a hypernova, leaving behind a supernova remnant and possibly a black hole. Even though it ranks as the smallest of the 4 giants in this countdown, VY Canis Majoris already defies human scale. Its measured radius, confirmed by direct interferometric imaging, places it far beyond anything the Sun could ever achieve. The story of this hypergiant is a reminder that, in the universe, size is often a symptom of a star's final unstable breaths, rather than a sign of enduring power. Number 3. Mu Cephei stands out not only for its staggering size, but also for the way it has captivated human eyes for centuries. Located roughly 2,840 light-years away in the constellation Cepheus, this red hypergiant is better known as Herschel's Garnet Star, a name born from William Herschel's 1783 observation describing it as a most beautiful object of a very fine, deep garnet color. Even today, that deep red hue remains visible to the naked eye on a clear, dark night, making Mu Cephei one of the most distinctive stars in the northern sky. Estimates place its radius between 1,260 and 1,650 times that of our Sun. To put that in perspective, if Mu Cephei were to replace the Sun at the center of the solar system, its swollen surface could reach well beyond the orbit of Jupiter, swallowing Mercury, Venus, Earth, Mars, and the entire asteroid belt. At the upper end of its size estimates, even Jupiter's path would lie deep within the star's outer layers, a scale that is almost impossible to grasp. Mu Cephei shines with a luminosity near 100,000 suns, and its outer atmosphere is so extended and unstable that the star pulses in and out over time. These semi-regular pulsations are signs that Mu Cephei is burning heavier elements in its core, entering the final stages of its life. The deep red color, the immense scale, and the visible variability all speak to a star nearing collapse, not enduring power. For astronomers and stargazers alike, Herschel's Garnet Star is a living reminder that the universe's most beautiful sights are often its most fleeting. In the second place, UI Scuti stands as a benchmark for the limits of stellar expansion. This red hypergiant, anchored in the constellation Scutum about 9,500 light-years from Earth, has become almost legendary for its sheer size. The commonly cited radius, around 1,708 times that of our Sun, places it in a class of its own, but the reality is even more remarkable. Scuti pulses, its photosphere swelling and contracting over a cycle of roughly 2 years. At its smallest, the star measures about 1,500 solar radii. At its largest, it may reach as much as 1,900. This means that if Scuti replaced the Sun at the center of our solar system, its outer layers would stretch somewhere between the orbits of Jupiter and Saturn, about 8 to 9 astronomical units from the center, enough to swallow every terrestrial planet, every moon landing site, every place humanity has ever set foot, and still keep going. Scuti's fame exploded in the 2010s thanks to viral size comparison animations that spread across YouTube and science channels. For many, this was the first time the raw scale of a hypergiant became something more than a number in a textbook. The image of a star so vast it could erase the architecture of our solar system in a single gulp is both humbling and unsettling. Yet, for all its notoriety, Scuti is also a case study in astronomical uncertainty. The star's distance, its true pulsation range, and the effect of thick surrounding dust all add layers of ambiguity to its final measurement. Even so, the currently accepted figures place it ahead of earlier giants, but still just shy of the reigning record holder. What Scuti reveals is that the largest stars are not stable monuments, but restless, dying objects, expanding, contracting, and shedding mass as they approach the end of their lives. Its story is a reminder that in the universe, the most staggering numbers are often provisional, shaped as much by what we can measure as by what we still struggle to see. And finally, in first place, Stephenson 218 stands as the largest known star by present measurement, a red supergiant so vast it almost defies analogy. Located deep in the Scutum constellation about 19,570 light-years away, this star sits at the edge of what our instruments can even detect. Its estimated radius hovers around 2,150 times that of the Sun, but the true range stretches from 1,900 up to 2,400 solar radii, depending on how astronomers measure through the dense veil of interstellar dust. Placed at the center of our solar system, Stephenson 218's bloated surface would extend just past Saturn's orbit, roughly 10 astronomical units from the Sun. That means Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter would all be swallowed whole, leaving only Uranus and Neptune orbiting outside the star's swollen edge. The sheer physical scale is almost impossible to internalize. A single star whose outer atmosphere could erase all the familiar architecture of our solar system in one engulfing sphere. Yet for all its size, Stephenson 218 is nearly invisible to optical telescopes. The star hides behind thick curtains of galactic dust, making it accessible only through infrared surveys. Its home, the Stephenson 2 cluster, is itself a cosmic anomaly, a gathering of red supergiants, each a dying giant, but none more extreme than Stephenson 218. This environment magnifies the challenge of measurement, as every calculation must correct for heavy extinction and uncertain distance, introducing a margin of error that is both frustrating and humbling for astronomers. The scientific debate around Stephenson 218's size is as intense as its physical presence. Its measured radius appears to break the upper limits set by current models of stellar evolution, the so-called Hayashi limit. In theory, no red supergiant should be able to sustain a stable envelope at this scale. If the measurement is accurate, then the models may need revision. If the models hold, then the measurement could be an illusion, inflated by dust, distance errors, or assumptions about the star's true temperature. Either way, Stephenson 218 sits at the boundary of what we know and what we still struggle to explain. One thing is certain, this is a star in the final act of its life. Like all red supergiants, Stephenson 218 will eventually collapse and explode in a supernova, scattering its elements back into the galaxy. Until then, it remains a hidden monument to the extremes of nature, a reminder that, even as our tools and theories advance, the universe still holds objects that stretch the limits of human understanding. Across all four titans, one truth emerges: the universe's largest stars are not signs of cosmic power, but warnings of stellar mortality. Their vast, unstable atmospheres reveal how even giants face collapse. That scale forced us to rethink what's possible. Which cosmic marvel should we rank next?